Hello my dear students, today we will go for the capacitor number 3, third class of the capacitor, in which we will consider three important concepts. So first concept we will find out the force between plates of a capacitor, second we will give energy stored in a charge capacitor, and third we will give an important concept, what happens when two capacitors at different potentials are connected together, how the charge can flow from one capacitor to another capacitor, and we will find out an expression for common potential. First we will go for the force between plates of a capacitor. See, now this is a capacitor, one plate is positive charged, another is negatively charged. This is plate number 1, say this is plate number 2. This is a parallel plate capacitor. Now being one plate is positive, one plate is negative, and the insulator in between them, then we think there must be a force of attraction between the two plates. The question is on what factors the force of attraction depends. Generally what happens, the force is for the Coulomb's law, K Q1 Q2 upon R square. R is the separation between them. So R is the separation between these two charges, plus Q and minus Q. Separation is D. So K Q1 Q2 by R square. And it is very important concept to see whether in this case force between two plates depends on the distance or not. First we should calculate the force between two plates. Now here let me consider the parallel plate capacitor having plate area of each plate is A and separation between them is D. Now this is a charge plate having charge plus Q, this is a charge plate having charge minus Q, the charge density plus sigma, charge density minus sigma. Charge density is charge per area. This is the charge density. Charge per area is the charge density. As per the applications of Gauss law, the electric field at any point due to a charge Q, the electric field at any point due to a charge sheet is given by sigma upon 2 epsilon 0. Epsilon 0 is the permittivity of free space, sigma is the charge density of this plate. Now you consider the positive plate. Now due to this positive plate, what happens? The electric field at this point is given by E equals to sigma by 2 epsilon 0. This is a formula derived in Gauss law. Sigma is the charge density of that plate and epsilon 0 is the permittivity of free space. Now what happens here? See, now at this point the electric field due to this is given by this one. Electric field being a vector, it is directed away from the positive charge. This is the positive charge plate. Electric field at this point is away from this charge. Directed away from this charge, that's why the electric field directions is in these directions. This is the electric field directions at this point given by sigma by 2 epsilon 0. So E equals to sigma by 2 epsilon 0, but the sigma equals to Q upon A is the area of the plate. So Q upon A, so that becomes Q upon 2 epsilon 0 A. This is the electric field in magnitude at this point. Now this plate, this charge minus Q being placed in that electric field, it experiences a force. We know from electrostatics, a charge Q when placed in an electric field, it experiences a force. The force given by the minus Q at this point is F is equal to QE. E equals to, you have a formula, E equals to F by Q. So F equal to Q into E. That's why here F is equal to minus Q into E because charge is minus Q. So this is E vector, this is F vector. Minus sign indicates that the force is opposite to electric field. Electric field is towards right. So force here X towards left means there is an attraction. The force in magnitude is QE in magnitude. Q is given by Q divided by this E has been substituted here, Q divided by 2 epsilon 0 A, that becomes Q into Q square 2 epsilon 0 A. So this is the force. This is the force on this plate due to positive charge. Okay, due to positive charge plate, the force on this plate is given by Q0 2 epsilon 0 A. With this is attracted towards this. Similarly, we can calculate the force on this plate due to this also attractive in these directions, but magnitude will be this much. The magnitude will be this much. So what is the important conclusions we are getting from this? You may be asked a question, what is the force due to a plate of a capacitor on another plate? With this force, these plates, first plate attracts the second. You can write, this is the force on second due to first, on second due to first. Same thing happens also, force on first due to second, same force will be calculated. And this force, see, this force does not depend on the distance between the plates. The force does not depend on the distance between the plates. There is no D factor here, and this was a question in 2018 NEET on what factors or force does not depend on these factors. Remember, force between the plates of the capacitor does not depend on separation between the plates. This is the important concept. You should remember this one. The most important concept, the force does not depend on D. This is the important concept. Force depend on charge, force depend on area of the plate, and force depend on permittivity. Force does not depend on separation between these two. This is an important concept. Now let us go for the second one. Now we will calculate the energy stored in a charged capacitor. Say, whenever a capacitor is charged, say this is the capacitor, same capacitor we can consider. Let me consider, there is a capacitor of capacitance C. Say, energy stored in a charged capacitor. So we will consider a charged capacitor. So this is a plate and this side is a positive charge, and we can connect this to a potential source or voltage source. One is positive, this is negative. So automatically this plate becomes positively charged, this plate becomes negatively charged. Now let voltage across this is V applied, voltage V applied across the capacitor is V. Now let charge stored, final charge stored across the capacitor is Q, and capacitance of the capacitor is C. Now whenever, see, initially what you do, you can connect a switch here. So switch. Now this battery is applied across the capacitor, but switch is off. Means no voltage is applied across the capacitor. Can you specify what is the charge on the capacitor? Charge on the capacitor is initially charge equal to 0. So what is finally? Finally charge equals to Q. That is the initial charge. I can say this is the final charge. So whenever switch is closed, the charge increases from initial value to final value. Now during this charging process, who does the work? This battery or cell, the source of EMF, does the work. It does the work. It spends its own energy to store the energy in the capacitor. So we will see how much energy is stored in the capacitor. Or battery delivers all the energy to the capacitor, or something is lost. Let us calculate the energy stored in a charged capacitor. Now here you can come to this point. At any instant t during charging process, initial charge is 0, final charge is Q. At any instant, let the charge is small q. Q is given by formula CV. C equal to Q by V. You know the very common formula for capacitance, Q by V. So at any instant during the charging process, let the charge Q equal to C into V, such that V, potential, V is equal to Q upon C. This is the voltage when the charge Q is stored across this. That is neither initial nor the final. It is the intermittent between minimum and maximum. मिनिमम एंड मैक्सिमम का बीच में एक चार्ज होता है. एट एनी इंस्टेंट दैट चार्ज बिकम स्मॉल क्यू. दैट स्मॉल क्यू इज अ चार्ज दैट इज CV and this is the charge at any time t. Then what happens? Now charge goes on increasing. Now for further amount of charge that is stored, let us take a very small amount of charge dq. dq is a very small amount of charge. So first work done to store next amount of charge dq. When the charge stored is q at any instant between the minimum to maximum, now further amount of charge dq, the work done will be this much, because you know the formula V is equal to W by Q, potential is equal to work upon charge. So it can be written as small amount of work by small amount of charge dW by dq. So dW, you can cross multiply this. dW is equal to V into dq. You can see here V into dq. I have written dW is equal to V into dq. Now see this V you can take from this formula, that is Q by C. In place of V you can write Q by C. That is Q by C into dq. This is the work done. This is the work done for further amount of work done to store a small amount of charge dq. Okay. Now then total work done to store the charge from Q to 0 to Q to Q, initial to final. The total work done can be obtained by integrating this expression from 0 to capital Q. Initial value is 0, final value is capital Q. At any instant t in between the minimum and maximum charge, that is Q by C into dq. We can write Q by C dq, integration 0 to Q. C being constant, C is constant, capacitance is constant. For a particular capacitor, as you have specified, capacitance does not depend on charge, capacitance does not depend on voltage. Then the C is constant. You can take out of the integration, like 1 by C integration Q dq. Now let me integrate it. Now if you integrate it, you see W equals to 1 by C integration Q dq, minimum charge 0, maximum charge Q, that is stored across this capacitor. This is V, the charge stored is capital Q, capacitance is C, and that Q is the charge at any instant t across this in between minimum to maximum. So that I think you know the integration Q dq, Q power is 1, that is Q square by 2. Q dq integration is Q square by 2, limit is 0 to Q. I think you know the process by which you can substitute the limits. See, Q is a variable, capital Q you can put for the upper limit should be substituted for this Q, and lower limit for the substituted for Q 0 square by 2, it is obviously 0. I think you know this process. Q dq integration is Q square by 2 from 0 to Q. First put the upper limit, write Q square by 2, minus put the lower limit, write 0 square by 2 is 0, that is Q square by 2C. That's why this work is done by this cell to store the energy at this. So this is the energy stored across this capacitor. This side is plus, this side is minus. This is the energy stored across the capacitor, and this work done is nothing but, we can say this work done is nothing but, we can say energy. This work is nothing but energy represented by capital E, that is Q square by 2C. So this is the formula. This is the energy stored across this capacitor as an electrostatic energy. Now Q equals to CV by definition. Q is equal to CV. That's why this energy equals to C square V square. Q is CV. C square V square by 2C. Now U equals to 1C cancels out. You can see half CV square. This is one formula. Okay. Now again V equals to, I have replaced Q is equal to CV, and you can write further Q is equal to CV. You can write C is equal to Q upon V. Now here you can write energy equal to Q square. C is Q by V, 2 into C is Q into V. Q cancels out, half QV. So this is one formula. See, this is one formula for energy Q square by 2C. See, this is one, this is second, this is third. That's why you can write the energy stored across a charged capacitor is half Q square by C, this formula, half this formula, CV square, this formula, half QV. So remember this formula for further explanations. That means in capacitor we are acquainted with these three. Generally in case of a capacitance, you will be given capacitance, charge and voltage. If you apply some voltage across a capacitor, then charge Q is stored across this, then they are interrelated by formula Q is equal to CV, and energy stored in terms of charge and capacitor and voltage, charge and voltage. So this formula, whenever charge and voltage will be given, this can be applied. Capacitance and voltage will be given, this can be applied. Charge and capacitance given, this can be applied to calculate the energy stored across the capacitor, and this is the numericals, and you can calculate it. If you know the capacitance charge, this formula should be applied. Capacitance and voltage, this formula should be applied, and charge and voltage, this formula should be applied. They are interrelated. But what is the most concept behind this? Here you see, energy we know generally conserved. And whenever you are applying a battery across a capacitor, the capacitor is charged. Battery consumes its energy, battery consumes its own energy to charge the capacitor. Question is, how much energy is stored in the capacitor, or all the energy that is supplied to this will be stored, or something will be lost? And you should remember the fact, whenever the battery is applied to a capacitor, 50% of energy is lost during the charging process in the form of heat. So this is the most important concept you can get here. See, the concept is, what is the energy supplied by the battery? Energy supplied by battery, W, I can write B equal to QV, because you know the formula V equals to W by Q. You know the formula V equal to W by Q. Potential is work to move the charge from one point to another. This is the definition of potential. So that W is equal to QV, that is the energy supplied by the battery. This is the energy supplied by battery. What is the energy stored? Energy stored across the energy supplied by the battery is equal to QV. What is the energy stored across this? That is half QV. So energy stored is equal to half QV, as you have calculated here. That means this is half of this one. That's why we can say 50% of energy is lost during the charging process in the form of heat. This is a very important concept you can get from this one, and to calculate the numericals, these three formula can be applied, nothing else. Okay. So with this, if you consider now the third concept. See, first concept we have covered, force between two parallel plates of a parallel plate capacitor, and we conclude it with a fact that, what are the conclusions? The force does not depend on the separation between the charges. Remember this one, charge plate. Second, energy stored in the capacitor, electrostatic energy that can be stored in the capacitor, and electrostatic energy that can be stored across the capacitor. By the consumptions of energy of this battery, the battery consumes its own energy to charge the capacitor, and 50% energy is stored and 50% energy is lost in the form of heat. These are the conclusions. Okay. Now, another important concept, as I have told you. So, we will finish this concept today. In the next class, we will go for, in next capacitor number 4, we will go for dielectrics. And most important part in the capacitor, so called the dielectrics. And after dielectrics, we will go for the final part, the series and parallel combinations of number of capacitors with and without dielectric. Now here we can see the sharing of charges. This is a very important concept, remember, sharing of charges and common potential. This is an important concept, remember, sharing of charges and common potential. This is very easy to follow. Say, now you consider any conductors. Now consider that there is a conductor or there is a capacitor, we can say. Capacitor may be a conductor, a spherical conductor, any type of conductor you can take, it has certain capacity. Now this is a conductor having a potential, this is a positively charged, say, and the charge is Q1. Now here, and capacity is a C1. Okay. Now capacity is C1 and voltage is V1 and charge is Q1. Another, you see, another conductor. They are not connected, remember, they are not connected, they are separated. This is Q2 and this is C2. Now this is the initial condition. Okay. Initial condition, Q1 is equal to C1 V1, Q2 equal to C2 V2. Total charge will be addition of these two. So total charge will be Q1 plus Q2 equal to C1 V1 plus C2 V2. Now let they are connected. See, they are connected by for example, a conducting wire. This is a wire. This is not a coil. This is a wire. Conducting wire. There are two charge body having certain capacity, certain potential, and they are connected at initial, and this is final. In final, what happens? They are connected by a conductor. What happens? This is one potential. This is another potential. Two bodies are a different potential, and we know whenever they are connected, the charges can flow from higher potential to lower potential. I think you know this one. Whenever you are having 2 points in an electric field having difference in potential, means strength, a body can move from high potential to low potential. In a similar manner, a charge can flow from high potential to low potential, but whenever the potential will be same, no charge can flow. That is equipotential. Thus, when the potentials are different, charges are different, they are connected. Now, the charge here becomes Q1 dash, here becomes Q2 dash. Okay. Now, the charge will flow from one potential to another potential. When they carry the same potential, capacitance cannot be changed. So C1 is the capacitance of one capacitor, C2 is the capacitance of another capacitor. So charge can flow from one body to another till they again attain the same potential. Again you see, whenever two bodies are different potential are connected by means of a conducting wire, charges can flow from high potential to low potential till they attain the same potential. So that here charge will be Q1 dash, Q2 dash, the final will be Q1 dash is equal to C1V, Q2 dash is equal to C2V. Now the total charge will be this plus this, C1 plus C2 into V. C1V plus C2V, V is common potential, potential will be same. The C1 plus C2, so the total charge here will be Q1 dash plus Q2 dash. If you add these two, you will get this one. But charge is conserved. That is a very basic concept in electrostatics. Charge is conserved. That's why we can say Q C1 V1 plus C2 V2, this charge must be equal to this charge C1 plus C2 into V. That's a V equals to C1 V1 plus C2 V2 divided by C1 plus C2. That means initially if you have a capacitor C1 having potential V1, capacitor C2 having potential V2, if they are connected by means of some wire, then what happens? Charges flow from one conductor to another till they attains the same potential. And common potential in these two conductors is this much. So this is a very important concept, and you may be asked some numericals over this one. See, I am showing you one circuit in which we can have a common potential and you can check it. Now here say there is a circuit like this. Say example, you will be given a problems like this. This is a very important problems. Your concept should be clear about this one. So here are two capacitor. Now here you can have a switch. See, this is a switch. You can close the switch. And two capacitors, that is a C1, this is a C2, and this is 2 microfarad for an example, and this is 3 microfarad. And this is a 200 volt, this is a 400 volt, and switch is open. Now there are two capacitors having C1 2 microfarad potential in this 200 volt, another capacitor 3 microfarad a potential 400 volt, and they are connected. Say they are not connected till now. Now if you press the switch, and they are closed. If you press the switch, they are closed. What happens? Now this is at high potential, this is a low potential. Charges will flow from high potential to low potential. Charges will flow from high potential to low potential till they attain the same potential. Here the question is find common potential V. It is V1, it is V2, it is V1. So here you can say, here given here you can say C1 equal to 2 microfarad, C2 is equal to 3 microfarad, V1 is equal to 200 volt, C2 it is equal to V2 equal to 400 volt. Okay. Now here you have to find out the common potential V. You can write common from which anything can be calculated later on. C1 V1 plus C2 V2 by C1 by C2. If you substitute the values here, if you substitute all the values, you will get that is 320 volt. Now you substitute C1 is 2, V1 is 200 volt. C1 is 2 into 300 plus C2, and you can substitute here. You can put C1 is equal to 2 microfarad, V1 equal to 200. But 200 into this becomes 400. Okay, micro plus this is C2 3, V2 400, that is 1200. The microfarad, this is microfarad, can be taken to farad is -6. C1 plus C2, 2 plus 3, 5. That means here this divided by 5 into 10 to the power -6. This cancels out. This is 1200 for 600, 1600. That 1600 by 5 340. That becomes, you can see 3, 2. You can substitute this to get the result. I think here the idea is clear. Whenever two capacitor of different charges and different potentials, we can say different capacitance are connected by means of some arrangement, then charges will flow from high potential to low potential till they attain the same potential and common potential. You should remember only this formula to calculate any numericals over this one. Okay, this part is over. I think in the next class we will go for next capacitor number 4. We will see the important part, dielectrics and effect of dielectrics on the capacitor. Thank you all. We will see again in the next class.